cylindrical coordinates, there are three variables: r, z, and theta. So we have to consider that u is separate function of r, separate function of z, and separate function of theta. And then this will be a little bit difficult, but still you can proceed. If you are not able to solve, then I am here to solve it. So in the last class, we were talking about the solution of the interior Dirichlet problem for a circle. Now the interior Dirichlet problem for a circle is important because from here we will get the idea what is the meaning of the Poisson kernel or what is the meaning of the Poisson function. So this is one of your important topic from your syllabus. So this is our aim, to define the Poisson kernel and Poisson, like both are same. So before that we are trained to solve this interior Dirichlet problem for a circle. So if we remind ourselves, then we were able to find out two solutions for this interior Dirichlet problem for a circle. Let me open the. So this was the equation and we have two cases. This was the equation and we have two cases. The case first, when this value is strictly positive, and the case second when it is strictly negative, and the case third will be coming that when k is equals to 0. So we are going to discuss that case. I think you guys were able to go through the solution and you could get how I am coming to the equation number 4b, sorry, how I am coming to the equation number 4b and how I am writing these solutions. So I think it is, if you have any doubt, then you may ask, because this thing from my side, I think that it is clear. But from your side, it should be very, very clear because this is a very easy topic. Okay? So if you have any doubt, then please ask. Or I am going to proceed because for as soon as I will be solving it for interior of a circle and exterior of a circle and then Poisson kernel, and I'm going to ask you to do the same thing for the interior of a cylinder, exterior of a cylinder, and then find out the Poisson kernel for a cylinder. Poisson kernel of a Dirichlet problem for a cylinder. So that is the thing which we are, and if you have any physical questions like, oh, I'm not getting what is the meaning of these things, how these terms are coming, so please do ask. Now case third was k equals to 0. Then we have r double dash plus r dash equals to 0. Now set r dash r is equals to v r to obtain. In the last case, if you remember, we were keeping here lambda square or minus lambda square, and this was divided by r, so that was passing to the right hand side. Because of that, this equation was Euler equation, and we have to make an assumption that r is e to the power j, one transformation of the variable from one space to another space. So it was little bit tricky to solve this equation, but here it is very easy to solve this equation because the right hand side is just 0, and if it is like this, then we can simply, either you can write it like this and or can solve, or you can make an assumption to make it easier. So r dash equals to v to obtain so r dv over dr plus, this is a linear equation. This is a linear equation. And what is the value of capital V? This is the value of capital V. So dr is equals to C1 dr over r. So r equals to C1 logarithmic of r plus another constant C2. And the second equation is h double dash h equals to 0. So h double dash equals to 0. H is function of theta, if you remember. It has been a very long time to go through the problem, so even I think I have forgotten. So don't worry about that. So h theta is equals to c3 theta plus c4. So the total equation of the system can be written as c1 logarithmic of r plus c2 and then c3 theta plus c4. Again, if we remind ourselves that this problem is defined at the interior of a circle, this problem is defined at the interior of a circle. It means r equals to 0 is the center of a circle that is coming inside that circle. So it is belonging to the domain. So whether we will be able to define the solution, this solution or not. Is it possible to define this solution?
Uh, for r equals 0. No, because log of 0 is minus infinity, right?
Exactly. So because of the appearance of the logarithmic term in the solution, we cannot define this solution. It means this solution is not acceptable. So we can see that we tried to find out three kind of solution. The first, when k was strictly positive, in that case we were getting the solution of this form. And when k was strictly negative, in that case we were getting the solution in this form. So because of the logarithmic term here, this solution is not acceptable. Next we are coming to the next form. Oops. So because of the logarithmic term, now someone can ask me, since logarithm is appearing with C1, so we can take the solution is C2 and C3 theta plus C4. But I would say that it is also not acceptable. So can anyone give me the explanation why I cannot take this solution? Can anyone explain me?
Maybe it don't satisfy the boundary conditions. I don't know.
And also at the same moment you can say that the solution should be the function of r and theta, and this is not a function of r. So with respect to r, its derivative is going to be 0. It means this function is simply going to be del 2u over del theta is equals to 0. It means it is going to turn to the ordinary differential equation. So this is also a way to say that this solution is not acceptable. Because in the last classes we were talking, oh, we can consider this solution because we can take C1 0. No, this solution is not acceptable, and the previous solution when we are taking k equals to minus lambda square, this is also not acceptable. So only acceptable solution is this one. Now again, keeping in mind that r equals to 0 is going to inside of a circle, because of that this term is going to be unbounded as soon as r is approaching to 0. So we have to take the coefficient C2 equals to 0 to make it a bounded solution. It means u r comma theta is equals to the explanation is given in your notebook. I have written each and everything, so that's why I'm not writing here because it is becoming very. Now the one condition or the periodicity condition, that the value of u at theta, and every time when it is covering 2 pi, every time it is covering 2 pi, the value is going to be same. So u r comma theta is equals to u r comma theta plus 2 pi. This is your periodicity condition. Is it clear? So C1, this does not make any sense because this is not so. C3 cos lambda theta plus C4 sin lambda theta is equals to C3 cos lambda theta plus 2 pi plus C4 cos lambda theta plus 2 pi. So C3 cos lambda theta minus cos lambda theta plus 2 pi, sorry, plus C4 sin lambda theta minus lambda theta plus 2 pi. Okay, so this can be written as C3 cos A minus cos A plus B. So sin, this is a trigonometric identity. I am not going to write the trigonometry identity. You need to write and you need to calculate. You guys are very intelligent. Minus C4 sin lambda pi and cos lambda theta plus lambda pi, that is equals to 0. So we can take sin lambda pi outside here. C3 sin lambda theta plus lambda pi minus C4 cos lambda theta plus lambda pi 2 sin lambda. I think 2 will also be coming. Is equals to 0. So either this quantity should be equals to 0 or that quantity should be equals to 0. So we cannot take this equals to 0 because sin lambda theta plus lambda pi is going to be equals to cos lambda theta plus lambda pi. So it will be a very, is it possible? No. It is only a theta equals to every time 45 when will be coming. So that's why we are going to take sin lambda pi equals to 0. That is lambda pi is equals to n pi, because at every integer value of theta multiple sin is 0. So lambda is equals to n equals to 0, 1, 2, 2. Now we have the solution. Where where is the solution? Yeah, where this lambda is integer value, this lambda is integer value, like lambda equals to 1, 2, 3, 4 and dot dot dot. So the total solution of the given partial differential equation will be the superposition of those solutions. It means summation of those solutions. Okay, so u(r), theta is equals to, that is basically Sturm-Liouville's problem. So every time when we solve the Sturm-Liouville's problem, we are going to add up those solutions because we get the solution which is in the even sum of integer or odd sum of integer. Cn C1 C3 cos n theta plus C4 sin n theta. Now we will pass this constant to C3 and then C4 and we will consider another new constant just for the sake of convenience. So Rn, take this as An cos n theta and C1 to C4 as Bn sin n theta. And without any loss of generality, when n will be 0, sine 0 will be 0. So, and r to the power 0 is 1. We will be left with a0, that is equals to u r comma theta. So, for the without any loss of generality, we consider a naught is nothing but a naught by 2. Just to make it a Fourier series. That is managed with the initial condition every time when you are solving a solved problem. So u r comma theta is equals to a naught by 2 plus summation and varying from 1 to infinite rn an cos n theta plus bn sine. I would like to ask you, don't forget to submit your assignment. I am just collecting those assignments in my folder. So when I will get time, I will calculate all of them and will upload the marks. So it is not that I am not watching those assignments. I used to see who is submitting and who is not. So which is a full range Fourier series. Which is a full range Fourier series. Now our aim is to find the constants an and bn, because still an and bn are constants which is left unknown to us. We have to determine an and bn, so that what is the boundary condition you had? You have the boundary condition ua comma theta equals to f theta. Is not it? This is the boundary condition given from this problem. So f of theta is equals to, just keep r equals to a naught by 2 plus summation and varying from 1 to infinite a to the power n cos n theta plus bn sin n theta. Hence a naught will be 1 over pi, because this is a full range Fourier series. So we are computing we are not going to solve the Fourier series because it is not possible. I am assuming that you guys already know that thing. And at some point, if you don't know what is the solution of the Fourier series, so you have the sufficient of internet. Now, if we keep the value of a to the power an capital An, an capital B, so basically an will be 1 over pi a to the power n and bn will be 1 over pi a to the power n. If we use the value of an and bn from this to this equation, say this is equation number 9, then we will get the solution. So can we change this theta, because this theta is a parameter, so can we change the parameter theta, phi, anything, like theta is to phi or psi? This theta is a parameter basically, we are like this. Can we write it, it is same? So just change theta to phi just to avoid any kind of conflict, because theta is also appearing here. So just to make it distinguish, I am changing this theta to phi. And then substituting the value of a naught, an and bn in the equation number 9, we will be getting u. We will see a very important result here. In fact, we can say that we are going to see a very beautiful thing here. You can see that we are getting the solution in the form of summation. Now we will write the solution in the form of integration. So basically in the term of the weighted function. So that is our aim to do here. R to the power n. I'm just sending this r to the power n inside of each. Cos n theta over pi integration 0 to 2 pi cos n phi d f phi d phi plus r to the power n a to the power n sine n theta over pi integration 0 to 2 pi sine n phi f of phi d phi. Okay, now can anyone tell me this integration is operating with respect to variable phi, so can we pass this cos n theta inside the integration? So just pass this cos n theta inside this integration and sine n theta inside this integration. So cos A cos B plus sine A sine B. What is the value of cos A cos B and sine A plus sine A sine B? I think it is cos of A minus B. So just pass this cos n theta inside this integration and this sine n theta inside this integration and take this limit outside. So cos A cos B plus sine A sine B into function of phi. So it will be cos A minus B function of phi. Then just going to the next page. I am going to use a lot of trigonometrical identity. It is not possible to explain all of them. Phi plus summation n varying from 1 to infinite r to the power n over a to the power n integration 0 to 2 pi cos of n phi minus n theta function of phi d phi. Now just take this integration, you can exchange the integration from the summation. So just take this integration outside of all. So integration 0 to 2 pi, and here I think 1 over pi was also coming. 1 over pi integration 0 to 2 pi and f of phi. So 1 over 2 plus summation n varying from 1 to infinite r over a to the power n cos of n phi minus theta d phi. This is your solution in a very compact form. Just take a look and tell me, do you have any question? Now we are going to obtain a closed form solution of this interior Dirichlet problem. So assume that C equals to summation n varying from 1 to infinite r over a to the power n cos of n phi minus theta, and S is equals to summation n varying from 1 to infinite r over a to the power n sine n phi minus theta, so that
La orden, my thesis
C plus iota S will be
would be impossible.
summation n varying from 1 to infinite r over n cos theta plus iota sine theta, that is e to the power iota theta. So e to the power iota n phi minus theta, or we can write it like summation. You will get to know why I am doing so. I am just making some kind of assumption. Iota phi minus theta. Please keep an eye on my calculation because I am very bad at calculation. So now since we are talking about the Riemann since we are talking about the Dirichlet problem on the interior of a circle. So if r is the radius of the circle, so what is the maximum radius of the circle? A. So r will be either less than or is equals to a. And since At r equals to a, the solution is basically of theta. So we are writing the general solution for the case r is strictly less than a. So r over a is strictly less than 1, and we already know that e to the power iota phi minus theta is less than or equals to 1. So c plus iota s is equals to summation n varying from 1 to infinite r over a e to the power iota phi minus theta. This condition is basically coming because at r equals to a, we have solution u of a comma theta equals to, because this is the boundary condition which we have provided in the beginning of the problem. So that's why we are taking that the general solution is written at the case when r is less than a. It is not equals to a, because as soon as r is equals to a, we have the defined solution. So every step should be very clear. And summation of this series. Can anyone tell me what is the summation of this series when the whole quantity is less than or equals to 1?
Ay, no entendí, Jota.
Something like 1 over 1 minus the
Summation
argument.
of, yeah, you are right, but just you are missing one thing. So summation of this series where x is less than or equals to 1 is x upon 1 minus x.
Yeah.
Yeah, that's what I was telling you that. So what will be the summation of this series? Can you see that it is using a lot of trigonometrical real expression? So you need to be very careful because you are going to do the same thing for the cylindrical flow. So just be careful and yeah. Now what I am doing, I am multiplying 1 minus r over a e to the power minus I phi minus theta and dividing it. So I have taken a shortcut in your notes. So when we will send this e to the power I phi minus theta inside this term, so it will be r over a e to the power iota phi minus theta minus r over a, and this e to the power iota theta to the power minus iota theta, that is 1. 1 minus r e to the power theta. 1 minus r e to the power minus theta. What will be the multiplication? Can anyone calculate it just for the sake of convenience? Because what I am feeling that the imaginary part will be cancelled out. What I know that 1 minus r e to the power theta, 1 minus r e to the power minus, just calculate it. It is equals to 1 minus r square, 1 plus r square minus r 2r cos theta, because sin theta will be cancelled out. You can calculate it. Just for your confirmation, I already know because I have written 2r over a cos phi minus theta. That was our aim, to make the denominator free from the iota, to make the denominator free from the iota, so that we can calculate the imaginary part and we can calculate the real part. So the real part will be the solution of the given equation, Laplacian equation. So that was our aim, and that's why I am doing so. So this is C plus iota S. Is not it? Now we know that what is this C? This C is this term. So if we calculate the real part of this equation, then that will be C, because the imaginary part is going to be S. Is not it? So If you have any doubt, even a small doubt, silly doubt, then you can ask. Equating the real part on both sides, we get C is equal. Basically, what was our aim? Our aim was to eliminate this summation so that we can write a closed form solution. To write a closed form solution, and to write a closed form solution, we have
We
to.
used the Fourier trick, right?
Sorry.
We used the Fourier trick.
To.
We used the Fourier trick.
Yeah, Fourier track. Yeah, in the same way. So this is our aim. You got it right. Yeah. Because sometimes in the Fourier series we don't go beyond the solution. We just write the series and say that it is a solution. We don't go over the closed form solution, if you remember. Some people go, but some people don't, because I did not. So what will be the real cos of phi minus theta plus iota sine phi minus? So iota sine theta sine phi minus theta will go in the imaginary part. So cos of pi minus theta minus r over a will go inside 1 minus 2r over a cos phi minus theta plus r square a square. So thus the expression in the square brackets of equation 10 becomes, so this expression becomes, oops, I'm going to the next page. And if you will add 1 over 2 to this, so it will be simply, and taking the LCM of this numerator and the LCM of the denominator, so a square will go to here. Or you can write this to outside of the integration. So this is known as Poisson integral formula. This is known as Poisson's integral formula for a circle which gives a unique solution for the Dirichlet problem. Say this is equation number 10a. The solution 10a can be interpreted physically in many ways. Now we can interpret equation number 10a in many ways. So when we are talking about a charge coming from an infinite distance, when we are considering about a potential charge coming from an infinite, so what was the equation of potential? The equation of potential was del 2 u is equals to some function of theta. So in that case, calculating this potential u is going to give you this Poisson integral formula. In the same way, if we are talking about the flow of heat in a sphere, if we are talking about the flow of heat in a circle, and we are calculating the heat at steady state, and we are calculating the heat at steady state. So what will be the equation of the heat at steady state? Del to u equals to 0. So u in that case is going to give you the temperature at the steady state. So it has many physical way. What kind of physical phenomena it is representing? You can interpret this closed form solution, this Poisson integral, in that way. So it can be thought of as finding the potential ur comma theta as the weighted average of the boundary potential f phi. So I'm just talking about the potential function. I'm not talking about the heat function. So it can be int, because basically when we are going to talk about the flow of a heat, then we are going to take a cylinder, mostly a cylinder or a sphere. So it can be thought of as finding the potential u r comma theta as a weighted average of the boundary potential. So this potential u r comma theta at the boundary is defined as u a comma theta equals to f sine f theta. So as a weighted average of the boundary potential f of phi, weighted by the Poisson kernel P given by this Poisson kernel P is given by P r comma theta is equals to a square minus r square over a square minus 2 a r cos phi minus theta r square. So if we are considering that this is the solution of a potential function, then for a given boundary potential f phi, this p r comma theta, that is the weighted of this Poisson kernel, that is the weighted of this Poisson kernel, is known as the weighted Poisson integral is known as the Poisson kernel. I am very confused between Poisson integral and Poisson kernel, so sorry for that. So this is your Poisson kernel. It can also be thought of as a steady temperature distribution in a circular disk when the temperature u on its boundary is given by u equals to f phi, which is free of time. So basically, when we are going to talk about the steady distribution of a temperature on a disk, and the steady temperature on the boundary is given by the function f phi, then in that case this is known as Poisson integral formula for a circle, which gives the unique solution for the steady temperature distributed on the disk, and this f phi will be known as the boundary temperature at steady state. Okay, so this is written in your notes, so that is the you can go over that. Next we are going to go over another topic. The Poisson kernel of the disk, I am going to give you the explanation, and then we are going to talk about the application of the Poisson kernel. So most probably tomorrow we will be talking about the application of the Poisson kernel, but still we can talk about the solution. And then tomorrow we will be also going over the solution of the Dirichlet problem on the exterior of a circle. On the exterior of a circle. Hi Ricardo. Ricardo, are you here?
Hi, teacher.
Yeah, so are you working in any kind of project? Are you working in any kind of project or any research problem? Can you hear me? Ricardo, can you hear me? Okay, so let's talk about the Poisson kernel of the disk. So when we are talking about finding the solution of a Laplace equation, so what is the meaning of finding a solution of the Laplace equation? Basically finding a harmonic function that is satisfying that equation. So finding the solution of the Laplace equation, either I am writing like this or I am writing like this. Finding the solution of a Laplace equation basically to finding a harmonic function in a bounded domain. And if we are in two-dimensional, so finding a harmonic function in R2 with given boundary value for the Dirichlet problem. Physically, one aims to find the potential function on the disk or on the in the domain R square whose boundary is bounded and the value of that potential function is defined on the boundary, or one aims to find out the temperature distribution in the domain R square where the temperature is defined on the boundary of the domain. So basically, we have to take the domain that is a bounded domain of R square. And if we are in Rn, then we are talking about the bounded domain of Rn. Because if we are not taking a bounded domain, then we will not be able to define the boundary condition. Is not it? So every time when we are talking about the Dirichlet problem, so basically the Dirichlet problem is finding out the solution of the Laplacian equation with a given boundary condition on the dependent variable u. Finding the solution of this Laplacian equation with the boundary condition which is defined on the dependent variable u. That is your Dirichlet problem. Newman problem is that finding out the solution of this Laplacian equation where the boundary condition is defined on the normal derivative of u. And Robinson, every time I forgot the name, sorry for that. So the Robinson problem is finding out the solution of this Laplacian where the boundary.
It's Robin, right?
Sorry.
It's Robin conditions, right? The problem is that in the last like 3 weeks, I have like introduced this misconception. It's not Robinson, it's Robin conditions, right?
No, it is Robinson.
Robinson?
Robinson is not it, Camilo? Just go over your notes. How you guys? I am not studying since a very long time, but still I remember about the Robin.
No, it's Robin boundary conditions.
Robin?
Yeah,
Robin.
I'm searching in internet. Yeah. It's
Serious?
one.
So why you are not knocking me?
I don't know why I was like reproducing this mistake, but I have like for the past 3 weeks referred to Robinson conditions, not Robin conditions.
Just wait. Let me verify because I am not agree with myself.
We can define the Robinson conditions.
Robin condition, sorry. Okay, so the solution of the
Ya le,
Laplace equation. I think I was reading some research paper, and I think Robinson is a very famous mathematician or something physicist, and I'm remembering him. I don't remember. So the Robin condition is the boundary condition defined on the dependent variable and also on its normal derivative, like in which direction we are taking it. So I used to remind you always, almost in every second class, what is the difference between three boundary condition. So consider the Dirichlet problem for the disk d alpha, where x is belonging to r square and modulus value of x is less than a. So this is a disk in two-dimensional with given boundary value h. H is boundary value. What I have explained through a problem, I'm just writing it in a generalized way, not for a circle exactly. Boundary value h to begin using the Laplacian in the polar coordinates. So every time when we are talking about the Poisson kernel for a disk means it has a coordinate where r is varying with theta, radius is changing with time. So you have to write your Laplacian in polar coordinates. So if you are going to talk about the flow in a cylinder, then you have three coordinates. First radius, z. What is z? Z is height, and then theta is the angle. So there will be three coordinates. So you have to change this Laplacian, like you are considering three-dimensional Laplacian problem. When you are talking about the Laplacian problem in a disk, then you have two-dimensional problem. When you are talking about the Laplacian problem in a cylinder, then you have three-dimensional Laplacian problem, and then you are changing it to the cylindrical coordinates. So be aware of these things. Again, I would say that you guys are very smart. So u r plus 1 over r u r plus. I wanted to ask you one thing. Can I open the notes and just read those things to make you explain? Because this is a theory. It is not. It does not have any calculation. I have given you the calculation already. I think I uploaded the notes like 23 and 24. So I have uploaded both. You can take a look.
23.
So for this Laplacian problem, which is written in the polar coordinates, it means it is defined on this disk where the value at the boundary is given by h. It means u a comma theta is equals to h of theta. So this is the boundary value. We find that for each n greater than or equals to the function Rn cos n theta and Rn sin n theta are harmonic, and as soon as they are harmonic function, we find out the solution in this form. So this is not a closed form solution. This is not a closed form solution. This is a general solution, like the superposition of n solution. N equals to 1, like integer when 1, 2, 3, 4, and then infinity. And substituting u a comma theta h theta, we are aimed to find the constant an and bn, and that will gives us 1 over 8 power n times the periodic Fourier coefficient of s theta. So just remind yourself what we have done to find out the solution of a Laplacian problem on the interior of a disk. Firstly, we write it in a polar coordinate, and then we find out the solution in the given harmonic function r to the power n cos n theta, r to the power n sin n theta, and this is not a closed form solution. Now still we are left with two constants an and bn, which is unknown to us. So we have the condition. One is the boundary condition, that is u a comma theta is equals to f theta, and one is the periodicity condition. One is the periodicity condition. So using those two conditions, we are aim to find this n and sorry no, we are aim to find an and bn, because in that case it becomes a full range Fourier series. So in that way we find the solution in this form. Now, using some sort of simplification, and trigonometric identity, we are arrived at this solution, which is free from the summation, So this is a closed form unique solution of the Laplacian problem, Dirichlet problem inside the disk. So using the law of cosines, we find the denominator equals. Now here the things may change. So using the law of cosines, if you focus on this denominator, so this denominator is equals to the distance squared between the point x r theta and y a comma phi. This is a distance in the polar coordinates between r theta and a phi. So basically just try to understand. I am drawing the figure. So this is your disk. Now this distance is a. This is theta and r is less than or equals to 0 or 1. So if we choose any point, suppose this is r comma theta and this is a comma phi. So the distance between these 2 points, r is varying on this chord. It's not it, r is varying on this chord. So r is variable and theta is some variable, r theta are variable, and a comma phi are fixed, because a comma phi are giving you the boundary condition r of a comma theta is equals to f of theta. So when we fix phi, it will be f of phi. So using this using these 2 points, if you are going to calculate the distance between the 2 points in the polar coordinates, then that distance is nothing but this distance you may calculate. Thus, the solution may also be written as more geometrically as an integral over the boundary with respect to arc length dsy equals to a d phi. So
The law of cosine.
just wait. R is equals to a x equals to a cos theta and y equals to a sin theta. So the distance between 2 points is this. So distance between 2 point x and y is basically modulus of x minus y. In the polar coordinate, the distance between 2 points is given by this, where x is equals to r comma theta and y equals to a comma phi. Is not it? So the distance in the Cartesian coordinate will be modulus of x minus y. Is not it? Okay, let me explain it in a more general way. I am saying that I am taking 2 points r comma theta and y equals to a comma phi. So the distance between modulus of x minus y is equals to square root of. Now we have the coordinates in the polar coordinates. We don't have the coordinate in the Cartesian coordinates. So in the polar coordinate, the distance is given by r square minus 2ar cos theta minus phi plus a square. So if we change again from the polar coordinates to the Cartesian coordinates, so square of this is square of this, because distance always comes with the square root of something. Like in the polar coordinate, it is easier to write under root x1 minus x1 2 square plus y1 minus y2 square plus g1 minus g2 square. So this term is nothing but modulus of x minus y square in the Cartesian coordinates when we are transforming from the polar coordinates to the Cartesian coordinate, and this r is nothing but the modulus of the x square. So the solution in the from the polar coordinates to the Cartesian coordinate can be written in this form, where h is the boundary value now, and this is the distance, and this integration was defined from 0 to 2 pi, 0 to 2 pi. So 0 to 2 pi, but radius is fixed. Radius was fixed, that was equals to a. It means we are defining this integration on the boundary. So del d alpha a square minus modulus of x square upon modulus of x minus y square hy dsy. So it can be written in this Cartesian coordinate. This leads to the definition of the Poisson kernel for the disk in the Cartesian coordinates, and hy is the boundary value, so the weighted function will be this one with the product of this one. Is it clear, or shall I explain it in another way? Only you have to check how to find out the distance between 2 points in the Cartesian polar coordinates. You may Google it. So when we are changing again it from the polar to the Cartesian coordinate, so it will take this form, and we know that if h is any point where
If I want to
then
do
the
my
rest
thesis.
of the
If I want to do my
integration, the
thesis.
rest of the integration is known as
If I
the
want to do
weighted
my
of that
thesis.
boundary value,
if
weighted function of that
I
boundary
want to do my
value, and the
thesis,
weighted function is known as the
if I
Poisson
want to do
kernel.
my
So what
thesis,
is the weighted
If I
function?
want to
1
do
over
my
2 pi
thesis.
if I
a
want to
square
do my
minus
thesis,
modulus of x square over modulus of x minus y square, because h is a boundary value where modulus of x is less than a, and what the
understand?
other coordinate was, we choose another coordinate y equals to a comma 5, so modulus of y equals to a. So if you have any doubt, then you may ask.
Understand this?
Till here, do you guys have any doubt?
What?
So
Give
if we are writing this weighted function as p x comma y, so this is also a way to write the solution of the Dirichlet problem, and where every time when you are finding the solution of a Dirichlet problem and this function that is defined on the boundary, then except that function, other functions are known as the weighted function for that boundary value, and the other functions are known as the Poisson kernel basically. And why we are calling it Poisson kernel, we are going to discuss that things, but we will discuss that thing in the Green's function, because Green's function is also one of our topic to discuss. Is not it? Now, one most important thing. What will happen if the boundary value is defined as 1? Note that if the boundary value h is defined as 1, this procedure would yield in both the cases the solution u equals to 1. The solution is u equals to, just keep the boundary value equals to 1. So this integration dy equals to 1 over the boundary where modulus of x is less than 1 will be 1, and this will also be 1. How it is coming? So if you are unable to do this in the Cartesian coordinates, so I am giving you an example. I was integrating from 0 to 2 pi Where is the solution? A square minus R square. A square minus R square over R square minus 2A R cos phi minus theta plus A square d over pi. Is it? D over pi. So for the case modulus of x is less than a, the integration, this is the well-defined integration. This is the well-defined integration. So the integration of this value is nothing but 2 pi, 2 pi a. So it will cancel out. Here it will be difficult to calculate this integration, but in the polar coordinates it will be easier for you to calculate this integral. And this is your homework for the day, to calculate this integral. Please do that, and if you are unable to do, then do ask me. So this is the case when we are talking about the Dirichlet problem on the exterior of a circle, exterior Dirichlet problem. So we are going to discuss the exterior Dirichlet problem in a very detailed way tomorrow, but not today. So it is for the time being, just calculate this integral. What will happen if you are taking the boundary value equals to 1? So when you will be taking the boundary value equals to 1, then your solution will be coming 1. So that is also because of the maximum minimum principle. So this is your way to analyze these things, because the maximum value can be attained at the boundary and the minimum value can also be attained at the boundary. So this is also coming from the maximum minimum principle. So this is your homework. What if we are taking the boundary function h is equals to 1? In that case we are getting the solution is 1. Can you relate maximum minimum principle for the Dirichlet problem? Do you guys remember maximum minimum principle?
Yeah, that the boundary conditions are continuously changing, right? No.
No. So just go over the maximum minimum principle. This is your homework. Just read the maximum minimum principle, mean value property. Firstly, mean value property, then maximum minimum principle, and then
The maximum principle says that the maximum of the absolute value of the function over the closure of the set is equal to the maximum of the absolute value of the function in the boundary.
yeah, maximum value. The maximum minimum principle says that the maximum or minimum of a harmonic function will be attained at its boundary. So that's what I'm saying, that when we are taking the boundary value is equals to 1, so u equals to 1 is going to be the solution, because in that case the maximum value will be 1 and the minimum value will be, like minimum I cannot say, but maximum is going to be 1. So in that case you will be getting the solution 1. So this is your homework to solve this integral. I am going to ask you for the calculation tomorrow. Yeah. And tomorrow we are going to solve the exterior Dirichlet problem. So I have uploaded both the notes 23 and 24. So 23 is basically the exterior Dirichlet problem for a circle. We will also see the solution of the exterior Dirichlet problem, and then we will be going over the applications of the Poisson kernel, where it is applicable, because we have read all the properties, strong maximum principle, mean value property, differentiability, and then we will be starting the green functions. Okay. So yeah, so let's see you tomorrow. Okay.
See you tomorrow, teacher. Thanks.
Bye.
Bye. See you tomorrow, teacher. Thanks.